In this class, we are going to discuss about the next concept, that is design procedure of clocked sequential circuits. Okay, so this concept is very important concept for long answer. Okay, so this is the last concept in our third unit. So please concentrate on this, and this design procedure of clocked sequential circuit is completely related to the numerical part. Okay, so that is nothing but problematical we are having. So now we'll see, if you want to design any clocked sequential circuit, compulsory we will follow some steps. Okay, so if you want to design any sequential circuit, so compulsory we need to follow some steps. So what are the steps we are having and what is the procedure we are having? So now we'll see here. Okay, so in that first step 1, that is nothing but a state diagram or timing diagram is given. Okay, so which describes the behavior of the circuit. So that means, so initially you are having a question. So that is nothing but problem we are having initially. So in that question directly they given the one state diagram. Okay, so in that question directly they given one state diagram or timing diagram is given. So that diagram definitely describes the behavior of the circuit that we need to design, and ultimately we want the circuit by using the flip-flops and also some combinational logic circuits. Okay, so for example, I will show that how to have how the sequential circuit will be there. So now I will show that. So already you know sequential circuit diagram. So now I will show that it will be concluded as sum of flip-flops and sum of combinational gates, right? So that's why whatever the sequential circuit you are having, so or how to design the sequential circuit means compulsory we need some logic gates, that is nothing but some combinational gates we need to use, and some flip-flops we have to use. Okay, so remember that the sequential circuit will be like this. Okay, so but in this problem the step 1 directly they cannot give the sequential circuit. We have to design that sequential circuit with the help of state diagram. Already you know state diagram how to look. So this is the state diagram look, right? So like that they given one problem. Directly the state diagram will be given as a problem. Okay, so what is the second step? Obtain the state table. That means for this state diagram we have to write the state table. So already I explained in previous case whatever the state reduction and state assignment method we are having. So in that already I explained ma. So see here directly in the problem they given one state diagram. So with the help of this state diagram we are writing the state table, right? So like that here also in the first step they given state diagram. In the second step what we will do? So find out the state table. Already know the procedure how to write the state table. Okay, so go and check it out once, state reduction and state assignment method. Okay, so that will help to write the state table. Okay, so now coming to the step 3. So that is nothing but the number of states can be reduced by state reduction method. So after getting state table, what is the next step? So we have to reduce the states, number of states. Okay, so we have already studied the state reduction method, and if you want to reduce the number of states, compulsory the two states will be similar. Okay, in state table if you want to reduce the number of states, compulsory two states will be similar. That means the present state and the next state values should be similar. So I will show them an example here. So see here, if you want to reduce the state table, so compulsory any of two states will be similar here. So just G and E, can you observe? So AF and here AF, in previous case we are having, so 0 1 0. That means present state values and the next state values will be similar in the state table of any two states. So compulsory we can eliminate that any one state in that. Okay, so see here, that is the state reduction method. So in the state table if you are having any two states will be similar like a present state and next state values, so then you can eliminate in one any one state. That method we can call it as the state reduction method. Okay, so now coming to the step 4, do the state assignment. Okay, so here do the state assignment method is nothing but if it is required, okay, if it is necessary, then you can go with the state assignment. Okay, so then no need of that state assignment means, so if it is not required, then no need to take the state assignment method. So already you know state assignment, that is nothing but, so after reducing the states, so then you can go with that state assignment. So state assignment means whatever the alphabet letters we are having in the states, so that will be eliminated with binary codes. Okay, so that is nothing but the states can be represented binary codes instead of alphabets. That is called as the state assignment method. So now coming to the step 5, determine the number of flip-flops required and assign letter symbols. Okay, so see here how many flip-flops we need, how many flip-flops will be required for designing sequential circuit. So that we knows from the state table only. Okay, so how to find out how many number of flip-flops we needed means, here how to find out that value means, depends on state table, depends on that state table only. That means in the state table we have the present state now. So present state, how many variables it consists, so depends on that we have to consider the flip-flops. Okay, so after that once the figure out, so that means once the flip-flops will knows, how many flip-flops will knows, so then it required how many flip-flops will knows means 2 numbers or 3 number of flip-flops may be required or 4 number of flip-flops may be required. So that figure you knows, after that you can assign the letters for that flip-flops. Okay, so if you, for example, if you are having two present state variables like a and b, so then in present state you are having in the state table a and b, so then automatically 2 flip-flops will be required. So then again assign the letter symbols for that flip-flop. So for example qa, qb, like that you can assign. Okay, so now coming to the step 6, so decide the type of flip-flop to be used. Here already how many flip-flops will be decided, right? So how many flip-flops will be required, that will be decided. So now coming to the step 6 is nothing but which flip-flop we are using. So which type of flip-flop we are using means, already the flip-flops are classified into 4 types. So 4 or 5 types, right? So just like SR, D, JK and T also, right? In that which flip-flop we have to use, that will be mentioned here. Okay, so for example if we are taking JK flip-flop, so then mention in the step 6, that is JK flip-flop we are using. Okay, so now coming to the step 7, so derive the circuit excitation table from state table. So here state table already we are having. Okay, so and so derive the circuit excitation table. So excitation table, how we will find it means, from the flip-flop truth table we are finding the excitation table. So in the step 6, that means before the step already we knows which flip-flop we are using. So for example if you are considering like a JK flip-flop, for that you have to find out the JK excitation table. Okay, which flip-flop you are using, for that only, with respect that flip-flop only you have to find out the excitation table. Remember that one. Okay, so now coming to the step 8, using the K-map, derive the circuit output functions and flip-flop input functions. Okay, so here we have to find out the K-map. So already I explained the K-map method. Okay, so with the help of that K-map, so we have to find out the Boolean functions here. So for what we have to find out the Boolean functions means, for output case, for flip-flop input case, we have to find out the Boolean equations. Okay, so now step 9 is nothing but derive or draw the logic diagram. So finally with the help of all these functions we have to find out the sequential circuit diagram. Okay, so in the last case, that means in the step 8 only we are getting the Boolean equations. So with the help of that Boolean equations we have to draw the logic diagram. Okay, so this is the procedure behind it, design of sequential circuit. Okay, so now let's see this procedure with one example. We have to design one sequential circuit. Okay, so let's see one example here. So see, we have one problem directly. Design the sequential circuit specified by the state diagram. Okay, so state diagram they given. So already in the first step they concluded, that is nothing but a state diagram or timing diagram is given, right? So already state diagram we are having the first step. So what is the second step we have to do? Obtain the state table. So now we'll find out the state table here. Okay, so this is the step 1 you have to consider. The problem directly we are having the state diagram. So now we have to find out the state table here. So step 2, we have to find out state table. Okay, so how to find out state table means first observe the state diagram here. So here in this generally state table consists of what? So it will maybe consist of present states, next state, like inputs and outputs. These are the general things the state table consists, right? So now we have to verify it in the state diagram. So what are there in that? First we have to verify. So here state diagram consists of generally 4 states, whatever the circle, what are the circle we are having, that means it consists of states. Okay, so how many circles you are having, that means represented as a number of states. Okay, so that is nothing but here 0 0 0 1 1 0 1 1. So totally we are having the 4 states, right? So 4 states is nothing but we have to consider as present state values will be 4 states. Okay, so and one more thing you have to observe here, after transition, that means from one state to another state we have a transition lines here like this. Okay, so this is the transition lines we know. So the transition line which indicated as the input and output lines, right? So the transition line will indicated as the input and output. So right here we have only input path, right? So just observe here. Here the state diagram consists of 4 states with binary values already assigned, that is 0 0 0 1 1 0 1 1. Since the directed lines, whatever the transition lines or directed lines are marked with a single binary digit. Okay, so this is a transition line is marked with a single binary digit without a slash. Okay, so without a slash. So we concluded that there is one input variable and there is no output variable we are having. Okay, so above the transition line or directed line, whatever we are having, so in that any information will be there through the directed line. So that information may be consist of 2 values, like with 0 slash 1 or 1 slash 0, like that. If you are having 2 values, so then we can say that one is input and another one is output. But in this state diagram we are having the directed line indicated as only single value, that we can consider as directly input only. There is no output path here. Okay, so remember that one. So that means this state diagram generally consists of present state values. Those are considered as whatever the circle having information, that will be considered as the present state. And next state we are considering, like here transition from where to where, that we will be considered as next state. And input here we are having only one value, that is either 0 or 1 only. Output we don't have here, so don't consider this output here. So now draw the state table. So that is nothing but first one I can consider present state. Okay, so this present state I can consider as AB, because here the circle, whatever the circle having information, so that is nothing but each circle or each state consists of the two informations here, like 0 0 0 1 1 0 1 1. That's why I can consider here 2 bits. Okay, 2 bits, 2 digits we are having in each circle. So for that case, the present state I can consider the variables A and B. Okay, so now consider as directly next state. Okay, so for this next state we have to show the input also. That input is nothing but I can consider here X. Okay, so this inputs here, how many inputs we are having? 2 information, that is either 0 or 1, right? Only 0 or 1 we have. So for that, one is considered as X is equal to 0 and other one is considered as X equals to 1. Okay, so X is equals to 0, X is equals to 1. For that, how to get the information, how to get the transition? So now we'll see here. So one is I can consider as for X is equals to 0, we are getting like A and B values, and for X is equals to 1 we are again getting the values will be A and B. Okay. So see here, the present state, which circle having the information, that means how many circles you are having the information, that will be considered as the states. So it may be consist of 2 digits or 3 digits or single digits, you have to observe. So based on that information, based on that digits, you can consider as the variables like A and B. So here 2 information we are having, no. So 0 0 0 1 1 0 and the last state is 1 1. Okay. Now, for x is equals to 0, the AB transition started from 0 0 to what? So x is equals to 0. That means 0 input. For 0 0 state I have to observe. So 0 0 state, x is equal to 0. What is the result we are getting? That is nothing but for x input 0, the transition, the directed line shows the itself only. That means same information it can shows. So that is nothing but the AB input will be again 0 0 only for next state. Like that, for x is equal to 1 of AB as 0 0. So for x is equal to 1, 0 0 information will be transmitted to what? So here 0 0 information for x input 1, it will be transmitted to which state? 0 1 state. Okay, both the values will be considered as AB values. So first 0 0 state, whenever the x is equals to input 0, so AB will be 0 0 transmitted to the again 0 0 only. Like that, if the input is 1, the 0 0 is transmitted to the what? 0 1 number. Like that, now coming to the second state, 0 1 state. So for 0 1 state, we have to observe x is equal to 0. What is the transmission? So 0 1 for input 0, the transmitted value to the 1 0 state. Okay. So now coming to here, 0 1 for one input itself only. Itself means same value will be represented. Okay. So now coming to the 1 0 state. 1 0 is nothing but for first 0 value. 0 is nothing but the transmitter line shows the itself only. The same digit can shows 1 0. And for 1, it will be transmitted to the 1 0 to 1 1. Like that for 1 1. So 1 1 is nothing but it will be 0. So whenever the input is 0, it will be shows the itself only. So same number we can shows. Next 1 1 for one input, it will be transmitted to the 0 0 path. So this is the state table. How to write the state table from state diagram means like this we have to write it. Okay, so this is the state table. Now the second step is also completed. So now we'll go with the third step. What is that? Number of states can be reduced by state reduction method. Okay, that means we have to do the state reduction method here. Step 3 is nothing but reducing this number of state. Number of states. So see here, this third step is reducing the number of states, right? So how to reduce the number of states actually? If the state table consists of any two states will be as similar states, then we can consider as reducing the states, right? So see here, this is our state table. So in that any two states will be similar here, check it out. So first present state, any two states will be similar, 0 0 0 1 1 0 1 1. So that means 4 states will be having different states here, right? So that means we can say that there is no state reduction possibility. Okay, we don't have that possibility here. That means there is no state reduction possibility. We can't reduce the states because each state is different here. Okay, so here 0 0 0 1 1 0 1 1. We don't have the similar possibility in the two states, any two states. Okay, so that's why in step 3 we can't reduce the states because there is no similar possibility. Okay, so this is the third step. So now coming to the step 4. So what is the step 4? We have to check it out. So step 4 is nothing but do the state assignment. So do the state assignment is nothing but here, how to do that state assignment means, first of all, state assignment means if any alphabet letters you are having in the state table, okay, in this information, okay, so in this state table, if you are having present state or next state or input, whatever that output values, consider as like alphabets, okay, if it is having alphabet letters, then you can convert it into the binary codes. But just observe here, each and every state we are having the binary only here, there is no alphabet letters. For example, I will show that. If you are having the state table is like this, A, B, C, D, E, A, B, C, D. So that means present state and input may have the only alphabet letters. So then only you can consider the state assignment method. So this state table will be right like this. Okay. So if the state table consists of alphabet letters, then you can consider the state assignment method. But in this state diagram, so in the state diagram or state table, we don't have that facility. So all the information consists only in binary format. So no need to take that state assignment table here. Okay. So already they mentioned here in the procedure, if it is required, then only will do the state assignment. But here there is no possibility. All the information consists only binary format. So no need to take that. Okay. So there is no, again here mentioned, no need to consider state assignment, because the state table is already in which format? Already in binary format. So no need to change that. So this is the step 4. And now coming to the step 5. Okay. So remember one thing ma, if you are having, for example, if you are having the state table will be consist of the states will be in alphabet letters, the further step we can't do like that. Okay. So that is nothing but we can't design the sequential circuit with the states of alphabets. Okay. In the format of state table consists of alphabet letters, we can't do the next step, because compulsory, if you want to find out or if you want to design the sequential circuit, so compulsory we can say that the binary information exists only. Okay. Okay. So now we'll go with the step 5. So that is nothing but determine the number of flip-flops required and assign letter symbols. Okay. So here how many flip-flops will required means, see here, state consists of each state, that means the circle consists of the information is 2 bits, no. So that means here each state consists of the 2-bit information. Okay. So then directly we can say that 2 flip-flops will be required. The present state information consists of 2 bits, no, 0001 1011. So this is the 1 bit and this is the 1 bit. So based on that we can say that 2 flip-flops will be required. 2 flip-flops required. Okay. So here we have a state, that means we require 2 flip-flops. Those are already I assigned in the state table, that will be A and B. Okay. So now coming to the step 6. What is the step 6? Decide the type of flip-flop to be used. Which flip-flop we have to use here means, generally, so here decide the flip-flop, no. So which flip-flop means, generally we are having 4 or 5 types of flip-flops we are having. SR, D, JK and T flip-flop, right. So here many digital systems are constructed with the JK flip-flops only. Okay. So number of sequential circuits are constructed with the help of JK flip-flops. For general applications we are using this JK flip-flop, and sometimes T flip-flops will be also used for a complementation purpose. Okay. So JK is nothing but in that we have the 4 operations, right. No change will be there, reset will be there, set and complement condition will be there. But coming to T flip-flop, it just having only toggle condition only, that means complement condition only there. And sometimes we are using D flip-flop also. Okay, the data flip-flop will be consist as reset and set conditions. So the two conditions will be also cleared in that. So that means we have to use JK, D and T also. So in that I am considering the JK flip-flop for general applications. So you can use this JK. Okay, so if you don't know T and D, so directly you can go with JK only. Okay, so if they are mentioned in the problem, directly design the sequential circuit specified by the state diagram. So that is nothing but they mentioned like that, design the sequential circuit with the help of JK flip-flop. So then in this place of step 6 you can mention the JK flip-flop because the problem is mentioned. In the problem only they mention, so that is using only JK flip-flop, or sometimes they mention like T flip-flop, or sometimes they mention like D also. Okay, so first read the problem is carefully. So after that, if they didn't mention, so that's your wish, JK or D or T. Okay, if they mention, that one only you can consider in the step 6. Here they didn't mention, no, so that's why I can use JK flip-flop. So this is for all purpose we are using. Okay, so now we'll see that next step, step 7. So what is the step 7? Derive the circuit excitation table from state table. So we'll find out the excitation table. Already I explained in the procedure. So how to find out the excitation table? So already flip-flop in the previous stage, flip-flop is decided, no? So for with the help of this flip-flop excitation table we are using here. So we know here which flip-flop we are using, JK flip-flop. For this we have to find out the excitation table. Already I explained excitation table how to take it. Okay, so go and check it out, flip-flop concept ma. Qn plus 1, J and K. So 0 0 0 1 1 0 1 1. Okay, here directly I will write the JK excitation table. So that means comparing one, I will show that excitation table also. Okay, so this is the excitation table concept. So here the step 1 is comparing with Qn and Qn plus 1, and step 2 is Qn plus 1 as our output verified in truth table. Okay, so already I explained this concept, go and check it out the video ma. So here the excitation table of JK flip-flop is this one. Okay, for 0 0 what is the result? 0 don't care, 1 don't care, and for 1 0 don't care, 1 don't care, 0. So directly I am taking here. If you need explanation, go and check it out that video. Okay, 1 don't care, and here don't care 1 and don't care 0. Okay, so 0 don't care, 1 don't care 1 and don't care 0. Okay, so this is our excitation table. So now derive the circuit excitation table from state table. So again we have to implement the state table here with the help of this excitation table. So rewrite that state table. So first one is present state I can consider. So that will be considered as A and B. And the next one, here I can separate the input values and next state values. Okay, so input is X value I can mention. Okay, and the next case is next state. Okay, next state. For the next state, what are the variables we are having? Again A, B only. A, B. So now here we have to mention, that is nothing but derive the circuit excitation table from state table. So now we have to write the excitation table values. So excitation table values is nothing but what is that? Flip-flop input values. Already knows, right? Here we have to compare the output with input. So input is our result. This is our result now. So that means flip-flop input equations. Flip-flop input equations. Okay, so this state table from excitation table. Sorry, excitation table from state table. Okay, reverse you can take it ma. Excitation table from state table we have to write it. Okay, again we have to implement the state table now with the help of this excitation table. So flip-flop inputs is nothing but how many inputs we are having? J and K, 2 inputs will be there. But here how many flip-flops we are taking? 2 flip-flops. So 2 flip-flops means first only the single flip-flop will be considered as 2 inputs. For 2 flip-flops, 4 inputs we are having. So J, K and again J, K. So this is the first flip-flop and this is the second flip-flop. So that means each flip-flop, each JK flip-flop consists of two inputs. One is J and another one is K. Here clearly mentioned in the step 5, 2 flip-flops we need. So 2 flip-flops we need is nothing but this JK will be consist as one input, that means 2 inputs, and another JK flip-flop we need means again another 2 inputs we need. So for that purpose I can consider as 4 JK inputs here. Okay, so how to consider in that means, so here first JK will be considered as the first inputs and the second JK will be considered as the second inputs of flip-flops. So in that first flip-flop input variable we can consider as A and the second flip-flop input will be considered as the B. So that's why I can consider here first one is A and the second one is B. Like that you can mention. Okay. So now we'll find out the state values. Okay, so now simply we can say that, see, for single input we have the how many variables? 2 variables, either 0 or 1. Okay, so like that we are having the states for input. So here present state, how many we are having present states? So 1, 2, 3, 4. So each one consists of 2 combinations. So totally 4 combinations we are getting. So 0, 0, 0, 1, 1, 0, 1, 1. Okay, so for x is equals to 0, 1, 2 possibilities we are getting now. So for that second possibilities also we have write the same condition. So already I mentioned here how to write it, how to take these values. Okay, so see here totally present state values we are having 2 conditions A, B, and the input we are having single only. So it may be raised as 2 conditions and it may be raised as 4 conditions. So for each case we have to mention the variables. Now coming to the next state. Okay, here next state how to consider means already they mentioned in the state table. For x is equals to what is the next state? For x is equal to 1, what is the next state? So here see, for 0, 0 condition, x is equal to 0, what? For 0, 0 condition, x is equal to 0, what is the transition? 0, 0. Now coming to the next one. For x is equals to 1, 0, 0, 0, 1. Like that. For 0, 1, x is equal to 0. That is 1, 0 case. Next, 0, 1 case, x is equal to 1, what? 0, 1.